So, we have been discussing about the energy theorems. Last time we talked about uniqueness theorem, superposition principle, then we proved the minimum potential energy principle, and also we have shown the proof of Castigliano's theorem. Let us now consider some more theorems. Today we will try to consider complementary energy principle. This principle is similar to minimum energy potential energy principle. In the case of minimum potential energy principle, we started with the minimum, we started with the principle of virtual displacement, and we proved the minimum energy principle, potential energy principle. Today we will try to start from the method of virtual forces and we will prove the complementary energy principle. So, let us consider again an object like this in 3 dimensions. It is subjected to forces, body forces x, y, z, and surface tractions Sx, Sy, Sz. These give rise to stresses sigma x, sigma y up to tau zx. Similarly, strains epsilon x, epsilon y up to gamma zx. Let us consider virtual forces delta x, delta y, delta z, which are functions of x, y and z applied to the whole body, and at the same time we also consider virtual tractions delta Sx, delta Sy and delta Sz applied over the boundary. Now, these virtual forces will give rise to virtual stresses. So, let us represent those virtual stresses. Virtual stresses like delta sigma x, delta sigma y, this will continue with all the stresses, 6 components of stresses. Because of these virtual stress increments, we are going to get internal work done. So, these are the internal stresses which develops, and it is going to work on the real strains. Therefore, we can now find out internal work done let us represent this internal work done delta u star, and that is equal to integral of the product epsilon x delta sigma x plus all the 6 terms up to gamma zx delta tau zx dV. The external work let us consider it to be delta W, and that is going to be integral of the product of virtual displacements, product of real displacement multiplied by virtual surface tractions. So, u into delta Sx, v into delta Sy plus w into delta Sz, and this is to be integrated over the whole surface. Similarly, we will also get the contribution from the volumetric forces, which are u delta x, v delta y, then w multiplied by delta z, and this is integrated over the whole volume. So, this gives us the external work done. Now, by the method of virtual work, we know that the sum of the internal work and the external work would be equal to 0. So, therefore, by the method of virtual work, we would have delta u star, and herein this is delta u star plus delta w equal to 0, and therefore, now we have seen that they are of opposite sign. So, we can write now delta in fact, we find that this is negative work done, and therefore, we can add here this way, and therefore, delta u star minus delta w equal to 0, and this u star minus w is nothing but complementary potential energy. So, this is delta pi star equal to 0, and this pi star is nothing but complementary potential energy. So, what we have found that if a system is in equilibrium and if they are subjected to set of virtual body forces and surface tractions, we are going to get variation of the complementary potential energy equal to 0, and therefore, we can now say that at equilibrium the complementary potential energy is stationary. So, finally, this means at equilibrium the complementary potential energy is stationary. It is similar to what we found in the case of minimum potential energy, delta pi equal to 0, and now in the case of complementary potential energy we have got delta pi star equal to 0. So, at equilibrium both potential energy and complementary potential energy are stationary. Now, we will consider another theorem which is very important theorem of elasticity. It is known as Maxwell-Betti reciprocal theorem or Maxwell-Betti reciprocal relation. Let me just state what it means. Think of a beam like this. If the beam is subjected to some force, let us say here at this location 1, a force is applied which is of magnitude equal to P, then the beam is going to give rise to some deflection at the point 2. If the force is now shifted from position 1 to position 2, then the deflection that will be produced at location 1 is going to be the same. So, what I mean that if P is acting here and if we have a deflection here of magnitude equal to delta, when P is shifted to location 2, we are also going to see a deflection delta at this location 1. So, this is reciprocity relation or this is reciprocity. Similarly, in the case of a 3-dimensional object also, if you think of it that you are applying some force at this location which is let us say R, and if this is going to produce a deflection here at the location let us say delta, and if we now shift and this delta is measured in this direction. Now, if we shift the point of application of the force R to this point and try to monitor the deformation at this point, it will be again equal to delta. So, this is reciprocity. It has also other way of specifying this reciprocity relation. Now, we will consider a general body like this, and let us consider that this body is subjected to forces. Let us say that it is subjected to forces like this. Here one force, we have another force acting at this point. Similarly, here also we have another force, and we consider that we have number of such forces acting on the body. So, we consider the set of forces to be given by, let us say, P11, this is P21, P31, and similarly P41, P51. Let us say that this force which is here is, let us say, nth force, and it is indicated by Pn superscript 1. So, if we consider now this set here, we have P11, P21 up to Pn1. This is the set 1. Now, if we monitor the deflection produced by these forces, let us say we monitor the deflection produced by these forces along these lines. So, let us consider that this is direction 1, 2, 3, and let us say we consider that m such directions we are trying to talk about. So, we will find that deflection along these lines, let us indicate them by delta 1 1 up to, there are m such directions. So, this is 1, this is 2, this is 3, 4, and let us say this is mth direction. So, we will have the deflection produced by the first set given by delta superscript 1 up to delta m superscript 1. Now, if we apply a set of forces now in these directions, let us say we would like to now apply force in this direction of magnitude equal to, let us say, P1 superscript 2, and here one force, let us say P2 superscript 2, and here also another force, let us say this is P3 superscript 2 and P4 and so on, and let us consider that we are applying a force here of magnitude PM2. I must mention that this deflection that we have got from the first system measured in this direction, it is directed in this direction, it is measured really in this direction. So, these forces, if we consider now second set, they are P1 superscript 2, P2 superscript 2 and PM superscript 2. So, what I am saying that now we are applying the set P1 superscript 2 up to PM superscript 2 when the first set is absent. Now, if I try to see the deflections along the line of action of earlier force P11, so this is the force P11, let us say that the deflection in this direction is delta 1 superscript 2. So, the force set, this force set produces a deflection of delta 1 superscript 2 along the line of action of P1. Similarly, we will have up to nth force and the deflection is delta n2. Now, According to the reciprocal theorem, the work done by the first set of forces on the displacement produced by the second set is equal to the work done by the second set of forces on the displacement produced by the the work done by the first set of forces on the displacement produced by the second set is equal to the work done by the second set of forces on the displacement produced by the first set. So, therefore, this is what is the reciprocity relation. So, we will write work done by the first set of forces on the displacements due to second set is equal to work done by second set of forces on the displacements due to the first set of forces. So, this is the reciprocity relation, and mathematically what it means is that P11 delta 1 2 up to Pn1 delta n2 is equal to P12 delta 1 up to Pm2 delta m1. So, therefore, in the second set we have m number of forces, and therefore, we are trying to consider m number of displacements along the line of action of those forces due to first set, and in the first set we have n number of forces, and therefore, we are considering the deflection along the same forces due to the second set. Now, we like to prove this theorem. Before we go into proving this theorem, I must mention that these forces need not be only direct tension or compression, it could be as well torsion, bending moment, it does not matter. The nature of forces does not restrict it to only tension and compression. Now, let us consider the proof of this theorem. For considering the proof, this theorem is applicable to both discrete and continuous system. So, we will consider now for simplicity a discrete system like a structure. Let us consider this planar framed structure. consisting of elements like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 and 11. So, these are the 11 members which are interconnected, each is a uniform member. Now, let us consider application of a force on this structure. Here, this is the force let us apply here in this direction P1, and we consider the deflection along this line. Let us say that the deflection along this line is equal to delta 2 superscript 1. Now, we remove this force P1 and we apply a force here at this point of magnitude equal to P2 and try to monitor the deflection along the line of action of P1. Let us say that this deflection here is equal to delta 1 superscript 2. According to reciprocal theorem, therefore, we must have P1 into delta 1 superscript 2 must be equal to P2 into delta 2 superscript 1. So, therefore, P1 delta 1 superscript 2 is equal to P2 multiplied by delta 2 superscript 1. Because of the, now let us consider how to get at this relationship, or let us prove this relationship. Now, if I am applying the force on this structure here, this will give rise to some forces in each of these elements, and if we consider that this element is undergoing some deformation equal to U1 and the member has an axial stiffness is equal to K1, then in that case the force that is going to develop, or the internal force that is going to develop in this element is going to be K1 into U1. Now, we will just try to consider superscript 1 to indicate that that is due to the force P1. So, therefore, if I consider now a force P1 is applied, then the internal forces that are going to develop in all these 11 members, they will be nothing but K1 multiplied by superscript 1, where K1 is the axial stiffness of this member 1. Similarly, we can write for the second element K2 U2 superscript 1, and therefore, we can write for all the 11 members like this. Last one would be K11 U11 superscript 1. Now, if we consider application of a virtual displacement in this direction of magnitude equal to, we have the force P1 acting and we have internal forces developed in all the 11 members. Now, we would like to consider application of a virtual displacement at this point in this direction of magnitude equal to delta 2 1. So, if we just apply this displacement, then this is going to cause internal forces, internal displacements or deformation in each of these members, and the internal, therefore, we will find now let us, I will repeat again, I must repeat this point again. I have the force P1 acting. Now, what I do is that I try to apply a displacement here, not at this point, of magnitude equal to delta 1 superscript 2. So, if we apply the displacement there, then we are going to get the work done, external work done is going to be given by P1 delta 1 superscript 2. Now, this displacement which corresponds to the force P2, it will also give rise to the deformation of each of these 11 elements which can be indicated by u1 superscript 2 up to u11 superscript 2, and therefore the internal work done is going to be, now we have already the force acting in the element number 1 is k1 into u1 superscript 1, and now we have some deflection or deformation of this element which is of magnitude equal to u1 superscript 2, and therefore this is the internal work done. Similarly, for all the elements, 11 elements, we are going to get the work done to be given by this expression. So 11th element has the force k11 u1 superscript 1, and now we have a deformation u11 superscript 2, therefore the work done is given by this. So this is the first case. Now let us consider that we have P1 is not acting, simply the structure is subjected to P2, so we apply P2, and we now consider the internal forces that comes up due to this. So internal forces if each of the elements are deforming to the extent u1 superscript 2, u2 superscript 2 and so on, therefore the forces that are going to come up are going to be given by k1 u1 superscript 2, and last element would have force k11 u11 superscript 2. Now we have the force P2 acting there, and we apply a virtual displacement along the line of action of P2, which is equal to the value delta 2 superscript 1. So the virtual work, so if we apply now virtual displacement delta 2 superscript 1, then the work done, external work done is P2 delta 2 superscript 1, and this is equal to the internal work done. So when we apply this displacement here, the internal displacements that are going to be produced in each of the elements are going to be given by u1 superscript 1, u2 superscript 2 and so on. Therefore the work done by the internal forces are going to be u1 superscript 1 multiplied by k1 u1 superscript 2, and this will continue up to u11 superscript 1 multiplied by k11 u11 superscript 2. Now look at these relations. So you have the expression here and here on the right hand side, they are the same, and therefore we have P1 delta 1 superscript 2 is equal to P2 delta 2 superscript 1. So that proves the reciprocal theorem. In fact, it can also be proved for continuous system, but that proof will be little involved. So this is good enough for you that reciprocal theorem means that the work done by first set of forces on the displacement due to the second set is equal to the work done by the second set of forces on the displacement due to the first set of forces. Now we would like to consider some example, very simple example to illustrate. So first example we will take it up like this. We take the example of a beam. This beam is of length L, it is subjected to a force P, and let us consider that the modulus of elasticity is E and the moment of inertia is I. So therefore the modulus of rigidity of the cross section is E into I. Let us see if we apply the force P here and try to calculate the deflection here at the point B, which is exactly at the middle, we can find that. So let us first consider the deflection. So therefore if the force is acting there, then the deflection equation for this case is going to be given by px square 6 ei into 3l minus x, wherein we are considering x to be aligned with the axis of the beam. So, if we now consider the deflection at the point B, which is exactly at the middle, so we put x is equal to L by 2. So, that gives us 5 PL cube by 48 EI. Now, if we consider the force to be applied at this point and we try to calculate the deflection at the point A, that can be obtained by the consideration that you just think of it that you have the beam here, and it is, if the force is acting here at this point, it is going to deflect like this up to this point, and then it is going to deform or deflect like a rigid element from this point to this point. So, therefore, from B to A, it is going to deflect like a rigid element. So, therefore, if we now calculate the deflection at this point, which is at L by 2 from the fixed end. So, if we consider that this fixed end is O, so this deflection at this point delta B, second case. So, we will like to write this is the second case, is equal to, we can obtain that deflection from the formula of a cantilever beam P L cube by 3 I, and therefore, this is nothing but P L by 2 cube by 3 I. So, that is the deflection of the point B under the action of the force P by 2 here. I am sorry, under the action of the force P acting at this point. Now, if I have to calculate the deflection at this point, we can consider deflection at A is nothing but deflection at B plus the rotation here at point B multiplied by this distance L by 2, and this rotation at the point B in this case is given by the formula P L square by 2 I, and therefore, it is P L by 2 square by 2 E I. So, that is the rotation, and therefore, we can now calculate the deflection at the point by adding up this or adding up the deflection due to this rotation to this one. So, therefore, delta at A is equal to P L by 2 cube by 3 I plus P L by 2 square by 2 E I multiplied by L by 2. So, we have got this delta A given by this relation, and this comes out to be P L cube by 24 E I plus P L cube by 16 E I, and the two together gives us 5 P L cube by 48 E I. 48 EI. So, therefore, we see that the deflection in this case and deflection in the other case is the same. Therefore, that is also as we expect from the reciprocal theorem, which states that if the force P is acting here and it gives rise to the displacement at the point B, and if the force is now shifted to this point, the deflection that will be produced at A is the same as in the earlier case. So, deflection produced by P at this point B is equal to the deflection produced by the force P at the point A. Let us consider another example wherein we have two forces, but now they are different. One is moment, another is a direct force. Let us now consider the same type of beam subjected to a bending moment m at the free end. So, let us consider that this is the set 1. And now, we consider another set where the P is the force acting at the middle of the beam. So, therefore, the second set is P. If M is acting here, then the deflection that is produced at this point is going to be given by, so M is going to produce a deflection along the line of action of P is given by, it follows the formula mx square by 2 EI. So, the deflection equation is mx square by 2 EI, and therefore, at this point L by 2 it is going to be m L by 2 square by 2 EI, and this gives us m L square by 8 EI. When P is the force acting here, that force is going to produce a rotation at this point or deflection at that point in the same sense as this bending moment. Look at this case, here the deflection curve is going to look like this, it is going to deflect and then it will remain like a rigid element from here to this point, and therefore, the slope here is going to be this one. So, that is produced by P. So, therefore, let us indicate by theta P. In fact, that theta P is same as the theta at this point. So, when you have a force P acting here, the slope produced is nothing but P L square by 2 EI, and therefore, we can get that from the formula P L square by 2 EI, and since L is L by 2, therefore, we will have P L by 2 square by 2 EI, and that is again equal to P L square by 8 EI. According to reciprocal theorem, what we expect is that work done by this M on the rotation produced by P. So, that is the work done by M on rotation produced by P, M into theta P, and the work done by the force P on the deflection produced by M. So, we will have, if we indicate that P and the deflection is delta M. Now, I think let me just also connect this way. Now, what we have really is that this is theta P. So, this is nothing but theta P, and this is nothing but delta due to M. So, if we now substitute the value, what we have, P delta m is ml square by 8EI and P into m into I am sorry m into P, which can be written P into m L square by, let me write this way, this is m into P L square by EI. So, you can see that both the expressions are same and they are equal, and hence it also follows the reciprocal theorem. Now, we will consider one example on the minimum potential energy principle. These energy principles are very useful in solving equations, statically indeterminate problems. So, let us consider application of the minimum potential energy principle for solving one statically indeterminate problem. Consider the case of a ring of uniform cross section. Let us say that the modulus of rigidity of the cross section is EI and the radius of the ring is R. It is subjected to tension, diametrically opposite tension. So, the objective is to find out what is the deflection of the top point with respect to the bottom point, and at the same time what is the maximum bending moment acting on this ring. So, if we now take a section of the ring along the horizontal diameter, and if we try to segregate that top half, we will see a picture like this. We have the force acting P here, and we are going to get, because of symmetry, we will have the reaction force here P by 2, and at the same time we are going to get some bending moment here. Let us say that is the bending moment m0 acting here. Similarly, this is the bending moment m0 acting here. Now, when the ring deforms under the action of the two forces, it is going to become elliptical. Maybe it will take a shape like this. So, it is going to take a shape like this, and you can see that herein the slope, originally it was 90 degree, and the slope is after deformation also 90 degree. There is no change in the slope, and therefore, the slope is unchanged, and we can write that the slope here at this point is equal to 0. So, if you call it A and B, you really have a case theta A, theta B equal to 0. Now, in order to solve this problem, it is first necessary to calculate this reaction moment m0. So, we can calculate that by applying the energy principle. Let us consider a sector of the ring here, this much, and it is making an angle of theta with the horizontal direction, let us say, and if I draw the free body diagram of this and show the forces acting on the sections, this is at before it is P and m0, and let us say that the force which is going to come up here is the force, let us say it is obviously going to be P by 2. So, we can write this thing as P by 2, and at the same time we are going to get a moment here. Let us indicate this moment by m theta. If we consider the equilibrium of this element from here to here, then we have m theta is equal to, it is m0 minus, this is p by 2 into this distance, which is r minus r cos theta. So, therefore, r minus r cos theta. So, therefore, it is 1 minus cos theta. So, that is the bending moment which is acting at this section theta. Now, if we consider the strain energy of deformation of the body, the strain energy that is here, that is nothing but du. Du is given by m theta square by 2 ei into the length of a element, let us say r d theta. So, if we consider a small element here making an angle of d theta at the center. So, therefore, the element energy is equal to m theta square by 2 ei r d theta. So, therefore, this total strain energy in the body is going to be, if we integrate this quantity from this point to this point and take the 4 times multiplication, that will give us the total energy. So, because there is symmetry here, the energy here in this sector is equal to energy here. So, also energy in this sector and also in this sector. So, therefore, we can write this total strain energy is nothing but, it is 4 times 0 to pi by 2 m theta square by 2 ei r d theta. So, this is equal to 2 by ei 0 to pi by 2. We have now m0 minus p by 2 r 1 minus cos theta into r d theta. So, that is the integration. If we are considering now the rotation at the point B or A, we can write that rotation at the point B to be given by theta B is equal to delta u delta m0, and in this case, since u is a function of both p and m0, we can write delta u delta m0 by Castigliano's theorem. So, if we now try to consider theta b, which is equal to 0, we now get delta u delta m equal to 0 equal to 2 by ei delta delta m0 of the integral 0 to 2 pi. We will not write the expression. So, I will just write the quantity within the curly bracket like this. So, this is what is we have last, we have of course r d theta. So, we will write this, that is equal to 0. So, now in this case you note that the quantity which is, I am sorry, here there is a square here. So, the quantity which is here appearing within the integral sign is not consisting of m0 as a variable of integration, it is a parameter. So, therefore, we can do the integration, or I am sorry, we can do the differentiation before the integration, we can take this differentiation inside. So, if we do that, and since this is 0, we can write now 0 to pi by 2 delta delta m0 minus PR 1 minus cos theta into R d theta equal to 0. So, if you do this, this gives us 0 to pi by 2, and this will give us 2, and m0 PR 1 minus cos theta, and integration of this quantity with respect to m0 is 1, and we have r d theta equal to 0. So, 0 to pi by 2, this is m minus PR 1 minus cos theta. We can take this out, 2 r also out, 2 also out. So, therefore, this is equal to 0, and if we integrate this, this is going to give us m0 pi by 2 minus PR, this will give us pi by 2, and this is sin theta, and sin theta 0 to pi will give us 1. So, that is equal to 0. Finally, what we find is that this m0 is equal to PR 2 by pi into pi by 2 minus 1, which is nothing but PR into 1 minus 2 by pi. So, the bending moment that is going to be occurring at the point B or A is going to be given by this. Yes, I think that we have one mistake here. This is, we have just to take care of this. We have missed this 2 here. So, if we carry forward these 2, so we have this 2. So, this will be PR by 2 is this. So, we get the bending moment, and therefore, you see, if the value for m theta we try to write, m theta is going to be PR, it is m0 minus PR by 2 1 minus cos theta, and now if I write PR by 2 1 minus 2 by pi minus PR by 2 1 minus cos theta. So, finally, this gives us m theta is equal to PR by 2 cos theta minus PR by pi. So, you get the maximum bending moment m theta maximum when this is equal to 0, and that is possible when theta equal to pi. So, therefore, this is, when you think of it, theta equal to 90 degree, then its value is equal to theta equal to 90 degree, it is minus PR by pi. you can calculate the deflection by considering the fact that so for deflection you want to calculate the deflection of this point. So what you do is that you consider these 2 points fixed and this is moving, and you can calculate delta p to be given by Castigliano's theorem delta u delta p. You can calculate u for this u, let us consider this u is equal to, let us say, u1, and this u1 is nothing but the energy of the portion 0 to pi by 2, this portion. So therefore it is 2 times m theta square by 2 ei r d theta. So you can calculate this energy of the half of the ring by this formula, and then if you differentiate this with respect to p, that gives you the deflection, and I would like to give you this deflection. You calculate yourself, it is going to be nothing but delta p is equal to pr cube by ei into pi by 8 minus 1 by pi. So you can apply the energy theorem for the solution of statically indeterminate problem, and you can also calculate deflections.